first, the usual things to introduce the speaker. I assume, well, I recognize most of the faces in the audience, so you probably know who I am. I work at KDAB, several roles, and we are hiring. So if you want to work at a company that does quite a few cool things and some really popular tools for C++, open source tools, just ping me and I'll forward you to somebody else. Because obviously I don't have the HR hat on top, and I forgot the email for our HR. So I also wrote a book that you might know of. It was translated into quite a few languages, some more popular than others, some that I understand and 4 that I don't. But it's really nice to see all the random squigglies around the code that I wrote. Apart from that, I'm a trainer, consultant, KD developer, and a university professor. Who cares, right? So Victor showed this already yesterday. I'm not, just a disclaimer for the disclaimer, I'm not really sure that this is Phil Wadler's quote, but I did hear him say it once, probably quoting somebody else, but I don't know who it was originally. So I always quote, I put Phil Wadler because of the nice picture that goes along with it. And the second disclaimer that I took really seriously this time is that this is slideware. The main part of preparing for the slides was actually removing references and stood colon. And now, whenever I see these slides, they kind of trigger OCD for me, because everything that I see something is like, oh, this shouldn't be okay, I removed forwarding. So the code is meant to present an idea, not to be the code that you're going to copy and paste to some other place. Now the question is, why a talk about expected? Again, in essence, to quote Clerks yet again, I wasn't even supposed to be here today, right? In essence, when the program for meeting C++ was published, after some time I was invited to talk about something. And I realized, okay, I looked at all the talks, nobody talks about expected, and at the same time, I was at Meeting C++ community survey, and there was a question, which type of error handling are you using? And obviously exceptions is the most popular one, and expected-like objects is the least popular one. And I thought I was safe. I'm going to present expected because it will be the only talk talking about expected on this conference. And then another a late edition, Timur's talk yesterday spent half of 1 hour and a half talking about expected. So still, I wasn't really that safe, even if I was able to invent my topic after all the talks were published. So let's start with a short introduction, because Timur didn't cover that. Usually, we use exceptions. We pretend that we use exceptions by throwing them, right? And we all know exceptions. We know that they have quite a few downsides. A lot of projects forbid using exceptions because of those downsides. Extremely slow, sad path, really optimal, happy path, but when you do the average, it kind of sucks. They add quite a lot of boilerplate to your binaries, even if you're not, if you don't think you're using exceptions. So usually in the embedded area, nobody enables exceptions because just the binary increase is 50% or something like that for those small devices, which is quite a huge increase. Execution paths are not that obvious because you can jump from a highly nested function randomly into something else. Most of us kind of know how normal functions work, how you call a function, you get something on your stack, and then you call a return, you get something in the previous stack. And with exceptions, my estimate is that maybe 5% of people at this conference know how they work internally. So it's kind of a little bit of a magic. And the worst part is that exceptions are quite easy to ignore. You love throwing them, but you never catch them. Well, at least most of the projects that I've seen exceptions in. And exceptions are not really a part of the API. We were told when we learned C++, in C++ everything can throw, right? So you don't see for each of the functions which function is safe, which function is unsafe. And while I do love noExcept as a C++ developer that likes performance, introducing noExcept was kind of, we give up. And not only C++ people, but the first talk that I saw about noExcept was by Herb Sutter. And he investigated, well, he found a couple of scientific papers that were talking about how people use exceptions, most notably in Java. Because in Java you have checked exceptions, you need to catch them. And if I remember correctly, it was 70% of all exception handling was either catch everything and ignore, or catch everything and just print out the message and then continue as normal. And noExcept is kind of our take on that. So yeah, we like throwing, and sometimes we do catch them, but yeah, usually we don't, so let's just put noExcept on a function if we don't want it to throw. Because obviously noExcept doesn't mean the function doesn't throw. It just means we are not going to check it, so crash my application, right? Now, even worse thing that came from our ancestors, the beautiful language called C, is since we cannot return several values at once or anything like that, let's return a bool or an int denoting whether the operation was successful or not, and then return the proper result via an output parameter. Obviously, this works very well. This is efficient, but the API is awful. And before we had no discard, the errors were as easy to ignore as in exceptions, maybe a little bit even more, because you didn't even need to write a catch or anything like that. In essence, if you forget to check for the result of the function, you're screwed. The next one, which is also, according to Making C++ community survey, a popular one, is to use special values in a certain type. Now the question is that a special value tied to the type itself or the usage of the type in some context? And unfortunately, even if we have some types that have built-in error values like not a number, there are even in the standard functions that return 0 as the error. So it's not even tied to the type. And for integers, sometimes we have positive integers are errors, sometimes negative integers are errors, sometimes 0 is the error. So it's completely muddy. You have no idea for a certain type, unless you read the documentation, what the values are considered special. And in this case, this is the easiest place to ignore the errors, because not even noDiscard helps. Because you're going to access the return value, and if it's a -1 denoting an error, you're just going to ignore it. And the compiler cannot help there. So in all of these examples, we kind of had something like all the functions, whichever error handling was used, they have a result or something else, or an error. And we have a class that implements exactly that. So a value type that can be either this thing or this thing. And it's std variant. Now, usually we mention Andre because we like him, and he was the first one to mention something like this in the C++ community. But in other communities, this is a really old idiom, that you can have a sum type of a value or an error and use it for error handling, especially for languages that don't come with exception handling natively. So before we get to the std expected, if you don't want to dive immediately, but you just want to dip your toes in the water, and you have your existing code that uses special values for errors, you can just write a simple wrapper type over those return values that will store the result and have some policy class that will decide if that value is an error or not. And then you can wrap C-style APIs into this thing. So for example, yeah, I'm blanking out, but for example, 0MQ library has some notion of error handling via special values for integers. You would be able to create your own result class that wraps, or your own wrapper for 0MQ, which would, instead of returning an integer, return an result of int and some policy that will, in the API, state which integer values are special. And even if it's stated in the API, you don't care. You can just call the hasValue member function, and the hasValue member function will rely on the validation policy to check whether that value is the special error handling value or not. For those policies, the most common ones are if a value is larger or equal to 0, then it's a proper value. If it's less than 0, it's obviously an error. The same thing, a similar thing for Unix usual return codes for applications. If it's 0, it's true or a valid result, and otherwise it's an error, etc. And in the last one, if a value returns true, it's a valid value when converted to a bool, and if it returns false, you can consider it an error. Useful for optionals, useful for pointers, useful for quite a few things. Any questions so far? So when you create a wrapper like this, you would be wise to add some member functions that are, let's say, commonly named. So hasValue to simulate the std optional, and .value again to simulate std optional. Even more, it would be even nicer to also support the pointer syntax like std optional does, so that you don't need to write all the boilerplate hasValue or something like that. So what we want to have in C++ is a variant that has the API of an optional or of the previously created thin wrapper. And that thing is called std_expected. Now, there are two proposals for std_expected. I call them the core proposal and the extensions proposal. I don't want to use the proper names because I don't agree with them, but the proposals are awesome. The first proposal kind of got in C++23 early on, but for the second one, it was really a whirlwind adventure of a romantic will day, want day, right? So it was proposed for C++23, but then it was postponed for 26. Then it got on the track for 23, then it was removed. It was a huge story how we maybe got the extensions proposal for C++23. Now, it's, from what I checked, it's not yet in the draft standard, but in Kona it was voted in, so we are going to, hopefully, if nothing bad happens, we are going to have all the things that most of the things that I present today in the standard expected. Now, since C++23 was feature frozen since summer, C++ community took the usual mantra of software development, it's not a bug, it's a feature, and turned it around. So it's a bug, it's not a feature, and we added a few features. So the extensions proposals was essentially considered a bug fix, although it adds quite a few member functions to std_expected. So let's see an example. If we have a function that returns expected of an email object or an error object, it's parsing some string and returns the email object. If the regex doesn't match, then we are going to return unexpected and the error. Since you can declare expected of t, comma t and use the same types, there needs to be some way to differentiate. Do you want to create a valid value containing t or an error containing t? So by default, expected is going to create values if you provide a proper type. And if you want to create an error, then you write this return unexpected and some value inside. So you can just think of it like std move hints that something should be moved. And in this case, unexpected hints to the expected that this will be the error value. Now, if we just use the core proposal, this is the API that we would have. So this would look kind of like the old C school where you check the result after each invocation of each function. You get some input. If input is not valid, then report an error. We will see how exactly. Then we are parsing the email, accessing the value inside of the optional because we already checked that the optional is valid. We can access it with the dereference operator. And again, if we didn't get a proper email but we got an error, we bail out. And the last one, we apply a function called format link, and we create a string that we return then to the caller. Now, it is worth focusing on this part here. So this is not the common idiom. The reason for it is that if the input is not true, it's going to contain an error, right? So we can just directly return it. But we can only return it if this type matches the return type of the function, which in this case it is true. So we have expected of string as the return type of the function and expected of string error t as the value that we are going to return. But in the second case, we have a parse email function, which will return expected of email object, and our function returns expected of string. And this will not compile. Instead, the idiomatic way is to always use return unexpected something.error. The previous code looked much nicer. The second code works, right? So I'm not sure what's better. Yeah, it's C++. And writing these things can be a little bit tedious. But that's the core proposal. The cool thing about expected is its predictable execution path. You can have as many number of errors flying in the air as you want. So again, no magic that needs to be inside of the compiler or the runtime in order for these things to work. This is just a normal value. You call a normal function, and you return a normal value. And again, since I said unlimited number of errors flying, another moment of silence for Teagle. OK, now before I continue, in C++, unfortunate, for the love of God. OK, breed. We don't have the uniform call syntax. So we have a few different ways to call functions when we have an object. It's either a member function, so we call it with the usual object-oriented dot something syntax, or we can have a non-member function, and then we call function of that object. Now, if by some weird coincidence the extensions proposal doesn't get merged, all the things here are still applicable. You can just write non-member functions. But with non-member functions, the syntax, when you have a few functions nested, is a little bit not something that C++ developers are accustomed to. So instead, all the following slides are going to use the range notation. If we ever get the UCS operator triangle, or you can just implement these on your own. Obviously, since I said we are not going to write any namespaces, you should put your weird things into a namespace, but on the slides, I'm just going to omit it. So if you have a desire to implement something like this and really use the pipe operator as the syntax for something, it's quite trivial. You just define the auto operator, a dummy object called SumFunction. And inside of the operator, you can use concepts to check whether SumFunction is a member function of a type, then call the member function, and otherwise just call SumFunction of an object. But this is not a part of this talk. The point is just that you don't get surprised when you see that everything is using pipe something, pipe something. Most of the time, you'll be able to use just a dot if the extensions proposal goes through. So we've seen this, and we said this is the idiomatic way to use expected. Again, tedious, but idiomatic. If we try to analyze what this function does, if we have an expected that contains an error, then we are just returning kind of the same expected. Maybe a different type, but it still contains the same error that the original one contained. And otherwise, for that thing expected and the value inside, we are changing that value into something else. And graphically, this should remind you of something that Victor talked about yesterday. So if you have a function that transforms strings into email objects, and you do this idiom on an expected that contains a string, you'll get an expected that contains an email. Quite cool. And if you do it on an expected that contains an error, you get essentially the same equivalent error. Now, the question is how we should call this function, this idiom, when we wrap it inside a function. And again, if we draw from the STL, we have this for vectors, it's called transform. We have this on optionals, it's called transform. And if the senders and receivers proposal is merged as it is, in senders, it's called dotted n. So use .transform. So email, pipe, transform, and pipe it through a format link. Now, this function, format link, is a function that takes a string, format link, okay, an email object and returns a string. It cannot ever fail. So it doesn't return expected of string, it returns a proper string. If we wanted to do something a little bit more complex, because we've seen that format link has 2 arguments, then we can just write a lambda. And again, we are kind of getting into the tedious part of the world. So as long as you have functions, named functions for everything, this dot transform or pipe transform is beautiful. As soon as you start adding lambdas, you're kind of going to get the usual C++ code that is not as nice and as readable. But still, this is quite a useful idiom. The second was we had also the parse email function. And unlike the previous one, this one does return expected. So it takes a normal value and returns the expected value. For it, we cannot really use transform. I'm not going to talk about why. You can see the talk from yesterday by Victor. So the difference is that we have a function that takes a string and doesn't return a proper value. It can return expected that has a value or expected that has an error. Okay? And in essence, what we need to simulate this is something that will take out the value from expected if it exists, apply the function, and return whatever that function returned. So it should be even easier than the previous one. We don't need to wrap it again inside of another expected. And again, if we have an error, we're just going to ignore it. And I think I'll need to speed up a little bit. And this function, again, if we draw from the already existing naming, For std optional, it's called and then, so we are going to use and then in these slides. Again, if you want to draw from the senders and receivers, it will be called let value. So use and then. So you can change these and say get input and then parse the email and then call, data transform, call the function called format link. Quite useful. And OK. Now the question is, what should we do in the end? We can return the expected to the caller and let the caller deal with the fallout. Or we can handle and create a fallback for the expected value. The fallback, in this case, if the value is not existing, replace the whole expected with an empty string, or the expected that contains an empty string. But usually, just imagine this is some web application for some strange reason written in C++. When you type an invalid email, you expect that the web page is going to say, OK, this is an invalid character in your email. You're not going to expect to know just an empty string. But at the same time, if you didn't type anything in, the web application shouldn't write this is an invalid email, which most of them do nowadays. Because if I didn't even start typing, of course I know that it's an invalid email. So what we want to do here is if we have a value, just leave it as is. If we have an error, then we want to do something with the error. And in some cases, we are going to, for example, return a string. If the email was empty, we are going to return empty string. And if the email wasn't empty, so we had some kind of error inside, we want to propagate the error. So we can just flip the previous figure around the axis. If the value is here, we do nothing. If we had an error, then we call a function that processes that error and can return an expected that has a value or expected that has an error. And it looks essentially like and then, but on the second argument. And in expected proposal, it's called or else. So after we have transformed, we got the potential error when parsing the email. We can just say or else. If the error specified was reporting to us that the email string was empty, then we don't really consider that an error. We are just going to return an empty string. By default, the default constructor of expected is going to default construct the value, not the error. And otherwise, we report the error in some way. So if you want to handle some errors, but not all, you can always use or else. Handle errors, and replace the error with a proper value. Otherwise, you just propagate the error onwards. Minute of silence for Teagle. Now the question is, if we are working with several libraries at once, and all the libraries, they don't use exceptions. We don't use exceptions and then definitely the other libraries won't. We can have libraries in our project that use exceptions, some that use out parameters, etc. We need a mechanism to convert between them. So for special values, I would first go for the thin wrappers. And then if you need to bridge them somewhere to some code that actually uses expected, then you just write the conversion functions. So the benefit of simple wrappers is that they don't take more memory than the value type. But they're not all powerful because you are removing some of the values from the domain and considering them special. As soon as you need all the values in the domain, then you're going to have to switch to something like std expected. So for exceptions, it would be quite cool to create an error type that is constructible from an exception pointer. And after that, you just write something like this. You write a function xtry that will take a function that can throw. It will check for all the exceptions, and if any of the exceptions occurred, we are going to return an unexpected of that error type constructed from the exception pointer. So wrapping the API that works with exceptions, it's quite trivial. Obviously, it's tedious because you would need to wrap all the functions, but that's something that you can use tooling to generate. In order to convert from expected to exceptions, you can just use .value. If the expected doesn't contain a value, .value is going to check and throw an exception. It's not going to throw the object that was denoted as the error, but bad expected excess or something like that. But at least it's going to throw an exception. Unlike that star value or dereference operator, it's not checking, so if you didn't check in advance, this will be a UB. If you have out parameters similar to creating an expected from an exception, you can create expected from the output parameters, and I'm not going to delve deeper into this code because it's boring. Now, if you have several libraries that use expected, but with a different error type, you would like to be able to convert between those. So in this case, we need something that, again, if it's a value, it remains a value. If it's an error of some type, we want to switch to an error of some other type. And I have to mention my favorite Unicode character in Terabang, the question mark and exclamation mark in the same place. So these are the two different types of errors, and we need some transformation function to convert an expected of one error type to expected of another error type. How would you call that function? Transform error. I have no idea what's it called in sender's receiver's proposal. So if you want to convert, you can just say transform error to error code or some other different type. Alternatively, you can just rely on the built-in conversion between expecteds. If you have an old error type that is convertible to a new error type, then expected of something old error type is convertible to expected of something new error type. So if you have the error types that are convertible between each other, you don't need transform error. Otherwise, you just write a function, a conversion function, and pipe it through transform error. So far, so good. Okay. And here we can see this thing in action. So get email link returns something that has error t as the error, and we want to assign it to my error t, which has a constructor that accepts error t. So it's convertible too. Also, since variants can be constructed from the types that they contain, you can also define my error t to be a variant of all the different error types that different libraries that you use provide to you. And then everything will just work like magic. But a magic that we know how it works, unlike exceptions. And these are the most important things in the proposals as they currently stand. Well, in C++ 23. But some of the examples are still not as pretty as we want them to be. We have transform and we have and/then, and both of them essentially accept a function that takes just a single argument. And this is obviously really cool in Haskell world. In C++, we often have functions that are multiple arguments wide, right? So we had this, for example. We have the email, and the email was expected. in a sense, if email can be empty, then email.user can be empty. So this is a function, format link, that accepts two values, and we are trying to call it with two expecteds, right? And for that reason, we have to wrap everything into a transform, a lambda, and all of these nice C++ characters on the slide. It would be really nice if we had a function that can, just like exceptions, if an exception arises anywhere, the function is not called, we're just going to drop out. Why don't we have something like, I want to call this function, where all the arguments can fail, and only if they all succeeded, we are going to call the original function with all the values from those arguments. So we can write something like that. We will call it xInvoke, and it will look, as far as the usage goes, something like this. So just like std_invoke, we first have the argument function that we want to call, and then the expecteds that should be evaluated before calling that function. Okay? Now the question is how to deduce the type of this huge thing. If we have expecteds that contain different types of errors, we can have different ways to return the final type. So we can force the user to explicitly specify the error type that they want, which can be tedious, but again, welcoming in some use cases. We can just take the first error type that we found and consider all of the types convertible to it and just ignore if they're not. Or we can just use std variant of all of them. Now the question is, if we have a list of types, how to deduce all of these? Imagine there is a library. There is, but you don't know it, so imagine there is. A library that works like ranges, but better without Nico's problems. And it works on template types, on type lists. So what we want to do is first create a type list of all the expected types. So we have expected of string error, expected of integer something, and we want to collect all those types in a list. Then we want to remove severe FT, so apply a function to it. So if we had const expected ref, it will just be expected ref in the following list. And then this line you can ignore for the time being. But the point here is that I've said we had a function and we want to call it with several expecteds. But sometimes you already have the values and you don't have the expected. So it would be cool if this type deduction thing could differentiate between an argument that is expected value and then handle it in some strange magical way, and a type that is already a proper value. We will see an example a little bit later. And in this case, we are just taking the first argument, the first expected type. If you want to have a variant, then you also need to pass it through the unique so that the types don't repeat, and then pass it to a meta function variant so that you get variant of and a list of types. But again, this is magic, and this is with dark background slide because this is not a part of this talk. But this can be done, and it's actually quite, it's not that difficult in C++ 20 and 23. And we're going to skip this one. So what xInvoke would look like, the first basic version, we find the error. If the error was found, then we don't even call the function that was passed to us. We just return that error to the caller. Somewhat like exceptions, right? If something through, then we are not going to call the functions, we are just returning the exception. The same thing goes here. Then we just construct, sorry, my mouse is on the wrong screen. We construct the expected, we call the function and pass all the values that we extract from the expected with this lambda above. So we have a list of expecteds. We use default expression to apply a function to all of them, extract value, extract value, extract value, extract value. And then we call that function with all the extracted values. Okay? And then we can call format link with something like this. Email.user is essentially pushing email to the transformation that calls user t : user, member function. And email is email. So we have two expecteds here, and we call format link function with two expecteds. Now we can add, since we, as I said, we want not only to be able to pass expecteds to the function, but also normal values, we can complicate the value for a function a little bit more and check again, if this type is an instantiation of expected, then extract value from it. If it's not an instantiation, then just return that as a value. And after that, we would be able to use the API like so. So for example, imagine that the format link also accepts the CSS class, whatever it's called, and then for the first two arguments are expecteds, and the last argument is just a plain string. And this is, at least for me, quite simpler than all the lambda thing. Usually, obviously, you're not going to have this. You're going to have separate instances of expected that don't depend on each other. Similarly, we can create X coalesce, if that's the pronunciation, where you have a list of expected values, and you want to call the function with the first one that is not invalid. If they're all invalid, again, we are returning an error. So you can treat this as some kind of a fallback. We have the main value, for example, high precision calculation of something. And if that one failed, we want to go to a hardware that was less precise, and if that one failed, less precise, etc. So a list of values, and you want to use the first valid one. How much time have I left? 15. Oh, cool. So we have X invoke and X coalesce. But usually, we also want not to even execute the code after some error has occurred, right? So we can also have X lazy invoke and X lazy coalesce, where you would be able not only to pass normal values, expected values, but also functions that return expected values, or ordinary ones. And for this, we can even complicate a little bit even more the value for a function. If the argument is invocable, then it's a function that will return us expected or a value. And after the last night's talk, I added the deducing this into the mix, so that this is the first example where I've seen that recursive lambdas are actually useful. So a lambda will call the function, the invocable that was passed to it, and then call itself with the result of that function, and then fall back to the second or third if branch. So if we have been passed a function, then the function will be executed, and the result will be treated either as expected or as a normal value. And if we got directly n expected, it will behave like it behaved before. And if it was a normal value, again, it will behave like it behaved before. Now, as Nico said, cool is not good, precise is better. The idea that you should magically differentiate between functions and non-functions can be quite problematic, and that's why in the standard we have find and find if, count and count if. We don't have the same thing that tries to figure out is this a predicate or not and then use it. Instead of that, you can create, again, a thin wrapper just like std_move or something like that, that will hint to xinvoke that you want to call this lazily. And then if we had some complex functions that calculates the CSS class, we can replace that string, the fixed string that we had, with a lazy of some lambda or lazy of some function. And then this API is quite clear and not smart, just like Nikolai likes. OK, so this part was a little bit probably more complicated. So any questions? If not, the last really lightweight part. You probably have seen this talk by this guy over here. So he talked about coroutines, and we all pretended that we understood coroutines afterwards. His presentation was awesome. You should watch it, but probably 3 or 4 times so to pick up all the things inside. Now, the reason why I'm showing this is that this code, if we apply a specific filter called the Freedom of Information Act to it, this code should kind of start to look like something that we already had. So we have this was a normal function, and this was the asynchronous function. So we have something here, so some value, I assume, and we have a lambda that does something with the result of whatever. So whatever is, we have a value, I don't care what it was, and then it's going to be processed, and after a while, it will produce a new value, and we call a lambda on it. If we try to, let's say, spell it out a little bit differently, this is a value that will arrive at some point in the future, and when we have that value, a lambda should be called. If that value never arrived, we should do nothing. If it didn't arrive because of an error, we should propagate the error. Does this sound like something that we already had? The only difference between what I just said and what we already had was this sometime afterwards. Coroutines don't care. In essence, for coroutines, if it's immediate or afterwards, it differs in implementation, and ask Andreas. But conceptually wise, it's the same thing. So, for example, for tasks, this is the code that is obvious what it does, right? We have a task again. In the future, we are going to get the result, and the result of the user task will be assigned to this variable. Obviously, I forgot the name of the variable. Cool. And then we can use that variable to create a new task. And again, for the resulting task, we do something. And then in the end, we return the name. Now, I just want to mention one small thing. Andreas said that coroutines cannot have normal returns. If they could, this would be much shorter. Because what we are doing here is extracting the name and then returning the name inside of a new task. And we already had the task name here. So the ideal world would be that we can just say return new name task. Instead, we need to extract the value and then co-return it and put it again into a new task, which is a little bit tedious, but okay, it works. And the code, theoretically, if we had a library that allows us to do this, could be written without any coroutines, just with and then. And here, it should be even more obvious that the last and then is completely useless. Essentially, we are taking the name and returning the name. Nothing more than that. So this should be possible in some future world. But again, this is not a talk about futures or coroutines or anything else, but about expected. This API we already have in expected. Just like we went from coroutines to this, it should be possible, and ask Andreas, to go the other way as well. So if we had expected, and we added coroutine support for expected, we could just write something like this. Get input, again, can return a value or an error. Then we co-await on it. Just imagine that co-await is not called co-await, but something pulled the value out of. Then it gets assigned to the string called input. Then we call another function that returns expected. Again, co-await, try to pull out the value from it, and continue processing. If any of these steps return an error inside of the expected, immediately the co-await cannot put the value, and the whole function just ends. And the whole function just returns expected that contains that error. So this is, let's say, 95% simulation of what exceptions do without the exception handling mechanism in the language. As soon as any of these co-awaits cannot pull a value, which means that the function that was called failed or threw an error, the whole function that uses the whole coroutine is going to end and return the same error.
Isn't this like a fancy point?
I promise that I'm not going to mention that name in the talk. That's another reason why I didn't write the names of the proposals for expected.
Okay.
Of course, it's a fancy bind. So all of these things, obviously the talk was mostly focused on std expected, but all the idioms with and, then, transform error can work with any type of error value or error type, like Boost.Outcome, leaf, etc. And also it can work quite well with values that don't have something or something, but that have both value and an error at the same time. Now, it might seem a little bit counterintuitive to have both a value and an error, but just remember your days when you learned physics. Often you had the result and the numeric calculation error next to it. So sometimes you do have both, and obviously you can complicate this even more and say we have a value and an error or a different type of error. But that's a little bit of an overkill. And all of these functions can be easily implemented for all of these. And if you use the pipe operator, then most of the implementations of and, then, or else, etc., can be implemented in a generic way to work on all of those types. So as a summary, you should put your errors inside of values, but not inside of the domain types. As Arnemert likes to say, your class shouldn't have isValid. The isValid state should be inside of a wrapper like expected or something similar. We've seen how to create interoperability between different error handling mechanisms, conversions, and how to easily compose functions that deal with expected values. And in the end, with the help of Andreas, we were able to even completely simulate the mechanisms for exceptions without the actual exception handling mechanisms. So I'd guess this is the end. As a small note, this is how you can contact me. I was also on Mastodon or Fediverse for a long time, but never active. But nowadays, I'm a little bit more active than I used to be.
Any questions?
Thank you for the presentation. And as you mentioned, the this technique can be used instead of exceptions, and exceptions are considered sometimes slow. But do we have any estimations? Is it faster with this technique or than with the exception or not?
Good question. So the happy path is a little bit slower than exceptions because of the branching if and else. The sad path is as efficient as the happy path. So it's a tiny slower in the happy path and significantly faster in the error path. There is, just before Guy's question, I forgot to say one really huge benefit of proper values that denote errors as well. You can serialize them to disk, you can send them to the database, you can send them over the network between threads, between processes, or anywhere else, which you cannot do with exceptions. And that's a really huge deal.
Thank you very much. That was a really good presentation I expected. I'm almost certain, I mean, I'm on the library working group, but I'm almost certain that Jeff's additional stuff will get through, but time will tell. As a follow-up to the performance question, I would have thought that the happy path would have, branch prediction would effectively eliminate all of the happy path costs that you're describing with branching, or am I missing something here? So
I would mostly agree with you. That's why I said it's a really tiny one. Branch prediction is really efficient, but is not as it's not the same as no branches, right? Yeah. So I would say it's, for most use cases, it's an insignificant slowdown. If you're Andre, then it's probably not.
So in Rust, we have something very similar with the result, and they have this question mark operator, they have this pattern matching, which helps a lot to deal with it. And also on the library side, I mean, it's not standard, but they have like this anyhow, this arrow. So it seems like really a lot of work went into it, and they thought clearly about it. Do you think in this state it is already like usable for, like really good usable for everyone without those parts?
So first, I just want to say credit where credit is due. These things existed for much longer than Rust does. And all the things that are in Rust, just like C++ steals good ideas from other languages, so did the Rust. I would say this is really useful. It would be nice to have, obviously, pattern matching, and maybe even some special operators in C++, but for operators I don't expect to, pun not intended, I don't expect to see them probably at any point in the future. Mostly what you can do by yourself is create functions and some DSLs that allow you to work more easily with expecteds. In essence, this was kind of a just smaller DSL, right? So I would say that they're 80% as useful as in other languages, with maybe a little bit more annoying syntax.
Last one? Okay. Thank you, Ivan.
Thank you.